Hi everybody. So last class we have studied with wave optics. So last class I have done an introduction about wave optics, and then we have done one very important concept, what we call as wavefronts. And also last class we talked about Huygens principles, and I told you last time that we are going to discuss the wave optics based on Huygens principles. So we would like to do so many wave phenomena, so many light phenomena such as reflections, interference, diffractions, and polarizations based on Huygens principles. So now I would like to start with what we call as refractions. All right. So before I start the refractions, last class we talked about two important concepts regarding Huygens principle. That is two different wavefronts. One wavefront is what we call as spherical wavefronts, or spherical wavefronts. Spherical wavefronts, and other wavefront is what we call as plane wavefronts. So these two are one and the same. That means the plane wavefront is a part of a spherical wavefront. That means if I take a long distance or large distance from a source, then the wavefront we receive from a source is what we take as plane wavefronts. All right. So if the source of an object is or if a source of a light is very far, then the wave that we receive from such an object or such a source is what we call as a plane wavefront. So this is what we have. So let me give you what kind of wavefronts looks like. So this is a plane waveform. This is a plane waveform. So this is what we call as a plane waveform. So if you are here, if you are observing this, and the source of light is at infinity, and you receive a plane waveform. So plane waveform looks like this. So it comes like this. Alright, it comes like this. After every time periods, one wave enters into your eye. So this is a concept behind a plane wavefront. So this is what we have. So we would like to discuss reflections based on taking that waves are plane waveforms. So now first I would like to do reflection of lights. All right. So we say that there can be two kinds of refraction normally we observe. One is that the light goes from a rarer medium to denser mediums. The other refraction is when the light goes from denser to rarer. All right. So both refraction we have done great detail in our ray optics. So this is what we have. So what I'm going to do is the main point we would like to do here is I would like to derive Snell's law from this using wave optics. So what is Snell's law? So let me write down Snell's law here. Sin I divided by sin R is what we call as the refractive index of second medium with respect to first medium. So this is what we call as Snell's law. So this is what we are going to derive from this refractions. Alright, so let's start something like this. I say AB is an incident wavefront. So I just say AB is an incident wavefront. I just say AB is an incident wavefront. Incident wavefronts, and this is a plane wave. It is something like this. It is something like this. And P prime is an interface surface. This is interface surface. So this is an interface surface. Interface surface that is between air and water. Between air and water. This is going to be our second medium. This is going to be our first medium. And AB is incident wavefronts, and angle of incidence, look at here. Angle of incidence is going to be I. So this is angle of incidence. And we know that when a light goes from A into a glass medium, speed is going to decrease. Look at here. V1 is a velocity in medium 1 and V2 is a velocity in a medium 2. V2 is velocity of light in a medium 2. So I just say that AB is the incident wavefront. So that means it incidence and angle of incidence is I. Now look at here. When a light enters into second mediums, alright, when a light enters into a second mediums, a refraction takes place. Now we would like to understand, we would like to draw refracted wavefront. So what we are going to do is, our job is to draw refracted wavefronts. So how to draw refracted wavefronts? Again, simple, right? So look at here. Tau is this is the time required to move wave from D to C. This is the time. All right, and V1 tau is distance between B and C. This is what we have. All right. Now look at here. Since the light enter into a second mediums, all right, V2 is the velocity in a second mediums, and V2 is less than V1. Here I just write V2 is less than V1's. Now we would like to see what is the distance traveled by a wave in a second mediums, right? So distance traveled in a second medium is going to be medium 2 is going to be tau V2, let's say V2 tau. This is the distance traveled in a second medium. So what we would like to do now here is, I draw a sphere. Let us draw a sphere. I draw a sphere with the radius. Alright. So draw a sphere from with center, let's say with center A with radius V2 tau. This is the radius V2 tau, right? So I draw a sphere. Alright, this is the sphere. Alright, I just show you a small surface. And then what we do is, what we are going to do is, I am going to draw tangent. Draw a tangent. Look at here. Draw a tangent from C to the sphere. From C to the sphere. Alright. Once I draw a tangent, this is the tangent. This is the tangent, right? And once you draw tangents, and then you join A and B. Alright. Then what you do is join A and E. And then I say the distance between A and E is what is equal to V2 tau. And this is what we call as refracted wavefront. So what is refracted wavefronts? Refracted wavefront is going to be EC. So EC is refracted wave fronts. So this is going to be a refracted wave fronts. And R is angle of R is angle of refractions, angle of refractions. So what is angle of incidence? I is angle of incidence and R is angle of refractions. Alright, so this is, now look at here. Look at here, now this is incident waveform and this is reflected waveform. You can see some bending. Alright, why? Because light travels faster in a first medium than a second medium. So in a first medium, light travels a greater distance. In a second medium, light travels less distance. So when you draw a sphere, and this is going to be a radius, and once you draw a tangent, we obtain a reflected waveform. So it is something like I just come here and this started moving little slower and this start moving little faster, and then you can get reflected waveform. So this is angle of incidence and this is angle of reflection. Now what we are going to do is we are going to find out what is sin I and then what is sin R. This is what we are going to do. Alright, so this is what we are going to do. So look at here. I say this is 90 degree. Alright, this is 90 degree and this is a normal line 90 degree and this angle is a common angle. This angle is a common angle, therefore this angle is going to be angle I, which is written here. Alright, this angle is going to be angle I. Now look at here, again I'm doing here, this is 90 degree, no doubt. I'm sorry, I will use red pen. This is 90 degree, alright, and then this angle plus this angle is 90 degree, alright. So therefore, this angle become a common angle, this angle become a common angle. So therefore, this angle must be equal to angle R. This angle must be equal to angle R. Alright, again I am repeating here. This is 90 degree, angle R plus this angle is going to be 90 degree, alright, and this angle plus that angle is 90 degree. Since this angle is common, so therefore it is, let's say this is angle 1, angle R plus angle 1 is equal to 90 degree, alright. And this is, let's say this angle is, let's say angle 2, and angle 2 plus angle 1 is 90 degree, which implies that angle R is equal to angle 2, therefore angle R. So angle R is angle 2, right? So once we obtain this, then what we can do is I use cosine formula, right? So that is, I say what is sin I? Sin I is equal to perpendicular divided by hypotenuse. What is perpendicular? BC divided by hypotenuse is AC. What is BC? BC is equal to V1 tau divided by AC. I put this as angle 1. And what about sin R? Sin R is going to be AE. Why? Because this is the base, this is perpendicular, this is hypotenuse. Alright, this is AC is hypotenuse. This is equal to V2 tau divided by AC, angle 2. Now I just divide this to sin I divide 1 divide 2 sin I divided by sin R is equal to V1 tau divided by AC multiplied by AC divided by V2 tau. Cancel out. Finally we get V1 divided by V2. So what is that? Sin I divided by sine R is equal to V1 divided by V2. And we know that V1 is velocity of light in our first mediums and V2 is a velocity of light in the second mediums. So now what I'm going to do is, let's say C is the velocity in vacuum, velocity of light in vacuum. Alright, therefore what we say that N1 is going to be C by V1. This is the refractive index of first mediums. This is what we have done in our ray optics, absolute refractive index. N2 is going to be C by V2, refractive index of a second medium, right? So if I do this, once we obtain this, V1 divided by C divided by C divided by V2. Alright, so therefore what is V1 divided by C? V1 divided by C, and what is V2 or VC divided by V2? Which is equal to N2 divided by N1. Alright, so I'm going to write at top, so sine I divided by sine R is equal to N2 divided by N1. This is Snell's law, and if I do it further simplifications, this is going to be, so this is Snell's law. This is a Snell's law. This is what we call as Snell's law. So we have derived a Snell's law using wavefront concept, and that is refraction from radial to denser mediums. Radial to denser mediums. Alright. Now what I would like to do is, what about wavelength when a light goes from a radial to denser medium? What about wavelength? Whether wavelength changes or not? This is what we are going to see. Alright. So what I am going to do now here is, I say that let's consider, consider BC is equal to one wavelength. This is one wavelength. Alright. Now if I say if a BC, the distance BC is one wave. If a BC is one wave, alright. And then what I'm going to do here is, when we talk about the definition of wavefronts, alright, all the point lying on the wavefront should oscillate in phase. That means then AE should be one wave, alright, should be one wavelength with different shorter wavelengths, with shorter length. Otherwise, the definition of that wavefront definitions won't properly hold, right? So therefore, look at here, this is going to be like this. Alright, so which is equal to, I just say which is equal to lambda 2. Alright, which is equal to lambda 2. They are of one wavelength of different wavelengths, single wavelength of different wavelength. So that means I would like to say BC is equal to one wavelength, and what is that? AE is equal to another wavelength. Alright. So now what is BC? BC is equal to divided by tau, and E is equal to, alright, so I just divide these two. Let's say BC divided by AE which is equal to V1 tau divided by V2 tau, which is equal to wavelength 1, wavelength 2. Alright, so that means these two cancel out. V1 divided by V2 is equal to lambda 1 divided by lambda 2. So this is true, right? So that means the wavelength becomes shorter when a light goes into denser medium. This implies that lambda 1 is more than lambda 2. All right. So when a light enters into a denser medium, wavelength is going to decrease. All right. Wavelength decreases. Wavelength decreases as light goes from rarer to denser. This is what we have. However, the frequency will remain same. Frequency means why? Because this is done in class 11. This is what we call as a C. Alright. So look at here. If a wavelength decreases, alright, and then speed of light also decreases. Therefore, this remain constants. Alright. So therefore, frequency doesn't change. So therefore, when a light or wave enters from rarer to denser mediums, wavelength is going to decrease. However, frequency remains same. Why frequency should remain same? This is the relations. Alright, lambda decreases, C should decrease. Why? Because C is constant. Alright, C should decreases. So if C decreases and lambda also decreases, mu, that is frequency, which remain constant. So this is all about reflection of light from rarer to denser. Alright, now I would like to discuss reflection of light from denser to rarer. Alright. So same explanation will do, but I won't be doing all this derivation, right? So now next, what I'm going to do is, this is what we have from a light reflection from denser to rarer. So I'm not going to explain every detail because what we have already done, but I'll do some explanation which is not there in a previous topic, right? So this is what I'm going to do, right? This is again A, B is incident waveforms and I is angle of incidence. I is angle of incidence, A, B is incident waveforms. Now look at here, in this case what we have is V1 is less than V2. V1 is less than V2. Why? Because medium 1 is denser. Medium 1 is denser and medium 2 is rarer. Alright, and then bending is away from normal, and I would like to prove you that how bending is away from normal from this expression, right? So look at here, again same, the tau is the time. Again, same tau is the time for a wave to travel from B to C. So B to C, the time taken is tau. Alright, and the distance is going to be V1 tau. So distance BC, which is equal to V1 tau. Alright, and now when the light enters the second medium, the wave travels little faster, right? Since the wave travels little faster, so the distance AE is going to be, and I said which implies that, all right, the bending is what? Bending is away from normal. This is bending is away from normals. Why? Because BC is less than AE. Why? Because light travels a greater distance in a rarer mediums or a second medium than first medium. So, and then again what I'm going to do is I'm going to draw a sphere with the center of A, alright, with the radius V2 tau. And then what I'm going to do is that I just draw a tangent. Again, this is going to be a tangent. Tangent. I draw a tangent from C to the sphere. C to the sphere. And I join this line. AE is a distance. And then I say that this is going to be a wavefront. So what is the incident wavefront? So AB is incident wavefronts. Incident wavefronts with angle of incident I, and then EC is reflected wavefronts with angle of refraction R. So this is what we have. Now what I'm going to do is, we can easily derive a Snell's law. This is what I'm not going to do. You can do it at home as a home assignment. Now look at here. Now I can straight write this sin I divided by sin R, which is equal to. Now what is the second medium? Alright, this is what I have. And this is what we call as N21. Alright, this is what we call as N21. Sin I divided by sin R, which is equal to N21. Medium number 2 is a rarer medium, medium number 1 is a denser medium. Alright, so now bending is away from normals. Now what I would like to do is, so let's say at critical angle, let's say if I say I is equal to IC, then R is going to be 90 degree. R is going to be 90. This is what we derive. So therefore, sin IC is equal to sin 90 degree divided by N21. N21 is refractive index of second medium with respect to first medium, where second medium is a rarer, that you should keep in mind. Alright, so therefore, sin IC is equal to, again I'm repeating, so N2 is less than N1 implies rarer to, denser to rarer. So this is what we call as, so now if I say if I is more than IC, wave fronts or wave front undergoes total internal reflections. Wave undergo total internal reflections. This is what we have. So now we would able to discuss total internal reflection even using wavefront concept. So this is what we have. So with this I have done with the reflection. Alright. Now what I'm going to do is I'm going to do reflections. So that too reflection by a plane surface. This is again very simple. Alright. Only thing you should know is how to draw a wavefront. This is the point, right? How to draw reflected wavefronts, how to draw refracted wavefronts. Once you know this, then things are very simple. Alright, now this is what I have. This is reflections. Alright. So this is a reflection taking place, reflection by a plane mirror, reflection taking place on a plane mirror. So now look at here. Now be careful, why? Because all diagrams in the same medium, so you may confuse, right? So I'll use color pen. AB is incident wavefront. Again I say AB is incident wavefront. AB is, so whenever you discuss, you should first identify which is incident wavefront and which is refracted wavefront. That you should keep in mind. Incident wavefronts. Wavefronts with angle of incidence I. With angle of incidence I. Alright, so this is incident waveforms. And now I say, since the light reflection taking place in a same mediums, reflections are taking place in a single mediums, alright, so since reflections are normally taking place, in a single mediums, velocity remains same. So therefore I just say velocity remains same. Velocity remains same. So therefore what it says, BC is equal to, let's say, take some time, let's say this is equal to V tau. Tau is the time taken from B to C. Alright, this is the distance. Now look at here, again, this is how wave travels, and once a wave, this is the first wave, the first portion of wave that incident on a mirror, and then what happens is that once it incidents, this start undergoing a reflection. It goes like this, and once this point incident on the C, then it all goes like this. This will go like this. All right. So look at here. I have a bigger book. So this is like this. Light, and then incident goes like this. Then, okay. Again I am repeating. Alright, so therefore what I am going to do is here. So in time tau, the wave, the A travels up to E. And I say that AE is equal to BC. Why? Because they are traveling in the same mediums, and they are traveling with the same velocities. So therefore I say these twos are same. So these twos are of equal distance. Then what we are going to do is, now we are going to construct a reflective waveforms. This is, so I draw a sphere. Alright, what I'm going to do is draw a sphere of radius, let's say AE, with center A. And then what I'm going to do is draw a tangent. Next is draw a tangent from C to the sphere. And then once you join, what I'm going to get is EC is what we call as reflected waveforms. Now this is incident waveform and this is reflected waveforms. This is written, right? This is incident waveform, this is incident waveform, this is the reflected waveforms. Alright. So now what we are going to do in this case is we are going to prove law of reflections. In the previous we proved law of reflection. Now here we are going to prove law of reflection. What is that law of reflections? So this is what I am going to prove. I am going to prove I is equal to R. How I am going to prove I is equal to R? This is what. Again I say that this is reflective waveform. This is incident waveform. Again I am showing you and then I will prove you, right? So this is how it comes. Once it incident on a plane surface or mirror, it's reflected, and this is how. After that it goes like this. It comes like this. It goes like this. It is same like this. This is same like this. Come like this. This is very similar to ray optics. Now the difference is that ray optic, the ray of light is coming. Here in this case, wave is coming. Look at here. Look at here. Again I am doing it. So this is what we have. Alright, this is all about reflection. Now I am going to prove you I is equal to R. And I told you very beginning of these chapters that the Huygens principle is geometrical constructions. Alright, so we will do again geometrical constructions. So what I am going to take is, I take two triangles, these two triangles, right? I take a triangles, this triangle, this first triangle I am going to take this C angle, C triangle, CAB, alright, CAB, alright, and then next triangle I am going to take is triangle EC, triangle EC, alright, this is like this, alright, A, C, E, this is this two triangle, and what I'm going to do is, I'm going to prove that these two are congruent triangles, these two are congruent triangles, right? What I'm going to prove is, angle CAB is congruent with angle ACE. And alright, how I'm going to do is again very simple. Look at here. This is angle of incidence and this is angle of reflections. Alright, this is angle of incidence and this is angle of reflection. I'm going to prove that I is equal to R. This is what, this is my things to prove. So what I'm going to do is, look at here. Alright. This is I. How? I take this triangle, look at here, this triangle, when I take this triangle, I take this triangle, look at here. Alright. One, then another one. Okay. So, what is the common? This is the common. This is common to both right angle, right? This is common to both right angle, right? This is common to both. This is common to both. So if this is common, then this angle must be equal to angle I. This angle must be equal to angle I. Alright. So again I am repeating here. So I take two right angle. This is a right angle. And this is a normal right angle. So this angle become a common to both right triangle. Both right angle, right? This angle. Alright. So therefore, what is this? This is going to become I. This is going to become I. And next, what I'm going to do is, I will take this R, right? This is R, angle of reflections. So next, I'm going to take this. Alright. So this is one right angle. Alright. And next, this plus this is also 90 degree. Alright. This angle plus this angle is also 90 degree. So since this angle is common, right? This is common angle. If this is common angle plus this must be equal to 90 degree. This common angle plus R is 90 degrees, and this common angle plus that angle is 90 degrees, which implies that this angle must be equal to R. Which implies that this angle must be equal to R. Alright, so this is what I have done. So once I prove that this is angle R, alright, to make not to confuse, I just write this is one triangle, this is other triangle. Now things are little easier to understand, right? So now angle I and angle R. So now I say that these two are congruent triangles. These two are congruent triangles, right? These two are congruent triangles. If these two are congruent triangles, which implies that corresponding angles are equivalent. If these two are congruent, why is these two are congruent triangles? 90 degrees. Alright, and this angle is equal to that angles. I is equal to angle R. 90 degree are common equal length. All lengths, right? AC are equal. Why? I'll just say because AC is common. Why it is a congruent triangles? Then 90 degree angle is 90 degree angle 90 degree. 90 degree is equal to 90 degree, and again AE is equal to BC, and then what else? And this distance must be equal to, right? Which implies that AB must be equal to EC, alright? Which implies that these two are congruent triangles. If these two are congruent triangles, then their corresponding angles are equal, which implies angle I is equal to angle R. What is the corresponding angle of angle I? This is corresponding angle of angle R. So therefore we say that angle of incident I is equal to angle of incident R, which proves the law of reflection. Alright, so this is what we have done. So this is how I proved, alright, law of reflections. Now what I'm going to do is, we would like to study refractions by a thin prisms and refraction by lens and all, right? So that means how to draw refracted waveform and reflected waveform. This is what I'm going to do now. Alright, so this is what I have. So refraction by a thin prism. So this is incident waveforms. Alright, and now look at here, when the light falls at these points, I'll draw this. And look at here, this portion can travel a greater distance. Why? Because this portion enters in a glass medium with a thinner glass medium. That means in a glass medium, light travels a lesser velocity. Alright, so therefore look at it at the same time. Alright, so when the light goes through this, alright, speed is going to be less. So the distance will be less. So at the same time, let's say at same time, alright, this light could travel this much distance, and this light could travel only that much distance. Alright, so we have to draw waveforms. Once you draw waveforms, so this is how reflection takes place. This is refracted waveforms. Why? Because a light takes, a light velocity is lesser in a glass medium. Since this portion of a light travels a lesser distance in a greater, denser medium, so therefore it travels a longer distance. And this portion of light travels greater distance in a denser mediums, and it travels a less distance. So this is what we have. So this is how reflection takes place. This is how reflection takes place. It is something like this. Goes like this, then it is how it goes. So reflection takes place. refraction take place. Alright. Now next I have another diagram. This is convex lens. Again, this is the incident plane waveforms. Again, I'll draw a plane waveform here. Look at here. These portions and that portion travel a lesser distance in a glass. Travels lesser distance in a glass. That means, look at here, when this portion reach here, and look at here, when this portion reach here, alright, when this portion of light reach at this point, only then this portion of light, this light would able to reach. Why? Because it travels lesser velocity in this medium, right? So therefore, once you draw this is what we have. And then this is again, the waveform tells us it is converging. It is converging waveforms. It is converging waveforms. This is converging waveforms. Alright, look at here. I say light travels a greater distance at these portions, greater distance this portion. Why? Because light travels a lesser distance in a denser mediums. Why light travels less distance here? Why? Because light is traveling entirely in a denser mediums. Alright, so this is what we have, converging lens. Alright, now next I have is this. This is convex as well as concave. Alright, this is converging and this is diverging. This is just the opposite. This is converging, I've written, and this is diverging. Look at it, this I've already explained, and here, this is the incident waveforms, and when the light reach here, and when the light, this portion of light, when the light reach at this point, and this portion of light travels a greater distance. Alright, so you can get like this. And as it goes like this, so this is what we call as divergence. This is what we call as divergence. And this is what we have for concave lens. Again, this is what we will look at here. The point is that light travels at equal distance, equal speed. All the waveform travels the equal speed. However, look at it, this is the incident waveforms. This is the incident waveforms. And once the light incident on these two surfaces, light comes like this, light comes like this. However, this goes on. When it goes on and when it reaches here, it will come out. So by the time these two light reach at this two distance. So therefore, again, I would like to do this. This is a bigger waveform, same waveform but bigger waveforms. All right. So this again tells that this is converging mirror. This is converging mirror. Why? Because this is concave mirror is converging, right? Where it is going to converge? It is going to converge at focal point. It is going to converge at focal points. Alright, this is written here. Alright. So this, and then what about reflection by a convex mirror? So this is, you can do this as a home assignment. Like this. This is incident waveforms. This is incident waveforms. And then it is going to reflect. However, it has to travels. By the time when a light from this side A, light from this side B, reach at this point, light at C already reach here. So this is how I am going to construct. And this is what we call as diverging in nature. This is diverging in nature. Okay, actually I have given this as a home assignment, but I have done it now. Alright, so this is what we have. So with this, I have done with reflection and refractions. Okay, thank you.